Ian Lancaster. I'm the technical lead for Bitumen, and I'm going to talk to you today about bitumen testing. Let's have a look at the world of bitumen testing. It's an area that's fascinated me as long as I've been in the industry, and I'm going to take you through a few different parts of bitumen testing. We're going to start by looking at the conventional testing. That's the testing that we have right now, which tends to be empirical or basic. I mean, it doesn't give us any real indication of performance, but they're well established test methods. Some of them are well over 100 years old, and so they are well established. And we find that they're used in current specifications, generally speaking, across most of the globe, certainly across Europe. We're also going to look at conditioning. Now, conditioning methods, these are not test methods as such, but they induce a change within the bitumen. And it's important to remember that bitumen is a living material, really. It's affected by the effects of heat and air, and over a period of time, under the actions of heat and air, bitumen can become harder. And it's important that we have methods available to us that allow us to simulate that aging. And we have a couple of different methods for doing that. We can look at short-term aging, which is the aging which is induced as we would expect in an asphalt mixing plant, or we can look at long-term aging, which is the sort of aging that the bitumen would experience when it's in a road, for example. We're going to look at some calculations as well. Some of the test methods that we use can be used to calculate other properties, so we're going to have a look at those. And then we're going to look at the state of the art, or the new test methods. These tend to be, shall we say, rheology based, and they tend to indicate they give performance related information, and they're not currently used in many specifications. Sorry, I'm getting some background noise. Does somebody have a microphone on? If you have got your microphone open, if you could just close that down, please, that would be great.
I'm having a quick check, Ian, trying to see
thanks.
if anyone, but I'll keep an eye on that. Yeah.
Okay, thanks. So let's look at conventional testing. And we're going to start with needle penetration, covered by European Standard EN 1426. And when it comes to specifications, needle penetration describes what we call the consistency of a binder at intermediate temperature. We can reduce that down to it being a very basic measure of stiffness. It'll give a very loose indication of the stiffness of a binder at one discrete temperature. And it's the oldest of all the bitumen test methods. It's over 130 years old. And prior to the penetration test being invented by a gentleman called H.C. Bowen in America, there was no real test method for bitumen other than for people to look and feel it. It's alleged in the historical papers that I've read that refinery quality control operators used to take a small piece of bitumen and chew it and bite into it, and that was how they developed how they knew the material was on grade. And there was quite some disagreement when the penetration test was invented. They said that it could never be as accurate as the way that they used to test it. It's 130 years old. It stood the test of time, has the penetration test. We carry out the penetration test by bringing a standard needle just to the surface of the bituminous binder. We allow it to rest on the surface. We control the temperature of the bitumen very, very accurately to 25 degrees. We place a load of 100 grams on that needle, and then we allow it to free fall for 5 seconds. And the depth of penetration that needle makes under those very precisely prescribed conditions of 25 degrees, 100-gram load, and a fall time of 5 seconds gives us the penetration number of the binder. And it's measured in tenths of a millimeter. So if that needle penetrates the surface of the bitumen by 200 tenths of a millimeter under 100-gram load for 5 seconds at 25 degrees, that is a 200 penetration bitumen. And it's used in specifications. It's used to establish grades within a lot of specifications. You can see on the graphic there what happens as the needle falls into the bitumen, but we've got quite a nice little animation now to show you. Here you can see the needle being brought to rest just at the surface of the bitumen, and the test is carried out underwater. We allow the needle to penetrate for 5 seconds, and then we have our penetration number at the end of it. And that is needle penetration, the oldest of all the bitumen test methods. Next, and the second most common test method really for bitumen and bituminous binders, is ring and ball softening point, EN 1427. In specification terms, we term this consistency of bituminous binders at elevated temperature. So penetration was consistency at intermediate temperature. Softening point ring and ball is consistency at elevated temperature. Well, we can again condense that down a little bit and describe needle penetration as a very basic measure of upper surface temperature of a bituminous binder. Bitumen changes its physical form according to temperature, and the hotter we get it, the more runny it becomes, the less viscous it will become. And there will come a point as we heat it up where it changes from a semi-solid material effectively into a liquid, and that is more or less what we describe as the softening point. We can only really measure softening point in the range of 28 to 150 degrees. Trying to measure the softening point any lower than that becomes very, very difficult. It's very, very important when we're carrying out the softening point test to have very, very precise control over the heating rate, or we can get some quite significant errors starting to creep in. So we really need to make sure that we control the heating rate very, very accurately. And softening point ring and ball is the second oldest of the bitumen test methods. You can see both in the photographs and in the graphic below how the test operates. We prepare a disc of bitumen. We then level that. We take off any excess. We cool it down. We place it into a liquid bath. Add a ball bearing to the top of it, and then we start this very controlled heating rate. And there will come a point where the disc of bitumen is no longer capable of supporting that ball bearing, and it will fall through and touch the bottom of the frame. So let's see that in action now. Here you can see a technician placing the balls on the center of those bitumen discs. Now this is time lapse, so it doesn't happen quite as quickly as this, but there you can see the bitumen starting to flow, and those two balls drop through and touch the base plate, and that gives us our softening point. Which brings us to our first calculation. So we can use penetration and softening point to calculate something called the penetration index. This was first proposed by two eminent bitumen technologists, Pfeiffer and Van Dormael, way back in 1936. And it gives us an indication of the temperature susceptibility of a bitumen based on penetration and softening point. It's only really applicable to unmodified binders, and what we can, it's not really an absolute, it's more an indicator. So a binder with a high penetration index will have low temperature susceptibility, and a binder with a low penetration index has a high temperature susceptibility. The equation shows you there how we evaluate it. So we take our ring and ball softening point and our penetration, we put it into that calculation there, and also on the bottom. So on this side, this is just by way of an example. We take a binder that has a penetration of 50 and a ring and ball softening point of 53. And if we run that calculation, that gives us a penetration index of 0.49. And that's fairly middling, is that. It's just an indicator. But that's one of the first calculations that we can do. So we've looked at intermediate, we've looked at elevated temperature. What about low temperatures? Well, again, as I said, with when we're talking about softening point, if we heat bitumen up, it becomes less viscous. If we cool it down, it becomes more brittle, more glass-like. And there will come a temperature where it becomes genuinely brittle. And this is what we call consistency of binders at low temperature. And we measure that using the Frass breaking point test. And in much the same way as the softening point test, the Frass breaking point test gives us a basic measure of low surface temperature. So we get upper surface temperature from softening point ring and ball. We can get low surface temperature from the Frass breaking point test. There are some issues with it. I will be honest with you, there are some issues with the Frass breaking point test. It tends to work reasonably well for unmodified binders, but for modified binders, if we introduce a polymer into the system, then they tend to underestimate the low surface temperature. And the sample preparation and temperature control is absolutely essential when dealing with the Frass breaking point. Tiny amounts of grease or dust can completely affect the result that we obtain. So sample preparation is absolutely critical, as is temperature control. In the test, we take a sample of binder, we place it on a very thin metal plate, and we ensure that we get a uniform covering of binder across the plate. You can see it in action in the image there. And then we cool it down and continue to bend it, to continue to flex it until it cools, as it cools down, and then eventually there'll come a point where a crack appears. And at the point that crack appears is what we call the Frass breaking point. Now, let's have a look at it. So here we can see it, again, done in time lapse. You can see the temperature is falling, the binder is being flexed. Let's run it forward, and eventually there comes a point where the sample cracks, and that is the Frass breaking point. And as I said, that's a very basic indicator of low surface temperatures, but it does come with its problems. Next, we look at viscosity. And viscosity is a very interesting concept. There's a reasonable argument to say that it's probably one of the most important properties of bitumen to understand, because it governs almost everything that we do. It governs how the temperatures that we pump product around. It governs how we coat aggregate to make asphalt, or filler to make roofing felt, or waterproofing membranes, and it's a very, very important part of our understanding of the behavior of bitumens. Within specifications, though, we only really rely on tests at 2 temperatures. And that's a little bit of a weakness in the current specification systems within Europe, because we miss quite a bit of information there by just relying on these 2 temperatures for specification purposes, which is 60 and 135. The 2 test methods that we have in our specifications are called kinematic viscosity and dynamic viscosity. They both operate in pretty much the same way. We have a capillary, and we allow the bitumen to flow through that capillary and measure the time it takes to go between 2 excuse me, between 2 precisely defined markers on the capillary tube, and from that we can calculate the viscosity at those discrete temperatures. With our kinematic viscosity, which tends to be measured at 135, or can be measured at 160, but it's more common to measure it at 135, we measure that capillary flow under the action of gravity. We allow the bitumen to effectively free fall through the capillary and measure the rate of progress it makes between those 2 timing marks. With dynamic viscosity, because it's carried out at 60 degrees, bitumen tends to be much, much, much more viscous. And so we have to induce the bitumen to flow. And we do that by attaching it to a vacuum. And that vacuum encourages the bitumen to flow through those 2 timing marks. So we have the ability with our capillary viscometers to measure the viscosity of bitumen at 2 discrete temperatures. And these 2 capillary methods, they're applicable, they're suitable for unmodified bitumens. They don't work very well at all if we have modified binders, polymer modified binders, wax modified, etc. So for those, we need a slightly different method, and we do that using a method called rotational viscometry. And there we can measure the viscosity of the binder at a range of different temperatures and a range of different shear rates. So that rotational viscosity, which I've mentioned in the slide here, EN 13302, is a more sophisticated method of assessing viscosity. And we hope at some point that viscosity method will make it into our specifications. The next method I'm going to talk about is solubility. It's important to know that bitumen is pure, if you like. It shouldn't be contaminated with mineral matter, coke, rust, any other form of detritus. So we need to have a method for ensuring how pure the bitumen is. It's also important to understand the solubility of the bitumen if you're doing any sort of binder recovery or mix analysis where you're trying to wash the bitumen away from aggregates and fillers and determine the content. You need to know about the solubility of the bitumen. EN 12591, the specification for paving grade bitumens within Europe, specifies that the minimum solubility for all binders is 99%. And we assess the solubility of bitumen by making a very dilute solution. Bitumen is peculiar. It doesn't like being filtered, so we have to produce quite a dilute solution. So we only produce a 2% solution, so that's 2 grams per 100 mils of solvent, and we filter through a glass powder, and we measure how much is retained on the glass powder. The solvents we use are either toluene or xylene. They have a good compatibility with the bitumen, and it makes it easier to measure the solubility. When we assess the solubility of a polymer modified binder, we have to rely upon the manufacturers to define a solvent, to define the best solvent to use to assess the solubility of their products, because it's too difficult for us to do that within a specification. Now, bitumen's a petroleum-based material, and we want to make sure that we handle it safely. One of the risks associated with bitumen, of course, is fire, because it's handled at elevated temperature. And we want to ensure that bitumen doesn't catch fire when it's in storage, during the process of producing an asphalt mixture, or in storage of that asphalt mixture in what we call hot storage bins. So we need to make sure that we have a means of understanding whether or not our bitumen is going to catch fire under those conditions. And we can do this using the techniques called flashpoint. Here we have 2 options in our armory. The most common is what's called the open cup, and you can see that in the picture on the graph there, and that's used for paving grade binders, hard paving, and PMBs. Or we can use closed cup. Now, the difference with a closed cup is that the flame that you can see there above the sample and the thermometer is enclosed. So, and we use that for soft cutback and flux bitumens. In the test, we heat our sample of bitumen up to around 28 degrees below the expected flash point. Now, that can be quite difficult to estimate if you're dealing with unknown samples. So it's always best to deal with known samples. We start then from our 28 degrees below the expected flash point, and we increase the temperature at a very precise rate. And then the flame that you can see in the picture is called a pilot flame, and that passes across the surface every few seconds as the temperature increases. And there will come a point where there is sufficient volatile material in the atmosphere above the surface of the bitumen to cause what's called a flash. And a flash is a circular flame that spreads out, and it's at that point, at that temperature, where, given a source of ignition, we could get a fire. Now, for most paving grade bitumens, the flash point is well in excess of 200 degrees, and we get most of our mixing temperatures are well below that. So we do effectively minimize the risks, according to of flash point and bitumen catching fire. But it's a very important parameter for us to know. So far, I've only looked at the test methods for paving grade bitumens, effectively. When it comes to modified bitumens, polymer modified bitumens in particular, we need other methods to describe the performance and behavior of the binder. So let's look at some of those. Let's look at some of those now. So, in addition to things like penetration and softening point, in our PMB specs, we're required to measure cohesion. And that's a measure of the elasticity or toughness of the binder. Now, there are 3 different methods for assessing cohesion of a binder. In the graph and the image on this slide, I'm showing you the force ductility test, EN 13589, because that's the one that is most commonly used to assess the performance of a PMB. There are 2 other methods, EN 13587, which is the tensile test. In principle, it's similar to the force ductility, but it's not very widely adopted. And then we have the pendulum cohesion test, which should only really be used for situations where the binder is subjected to extreme stress, and that's for applications such as surface dressing, or for, if we've got anyone online from the States, chip seal. Yeah, so where we have quite an extreme stress that can be applied to the binder. But the most popular one, and the most common one, is our force ductility test. We do this at a range of discrete temperatures between 0 and 25 degrees. We stretch our sample of the binder. In the picture there, you can see 3 strands of bitumen that are being stretched and stretched and stretched. As we pull the sample apart, we measure the force. And if you look at the graph, typically we see an increase in force at the start. That tends to come down, and then it will increase again as the elongation takes place. Now, we only measure the cohesion between 200 and 400 millimeters extension. Everything outside of that we don't consider at the moment, and we integrate the area underneath the curve between 200 and 400, and we compute a cohesion value. And in specifications, we have a number of different classes ranging from greater than equal to 0.5 up to greater than equal to 3. Because we have a combination of cohesion energy or cohesion value and temperature, it's very difficult to make comparisons between binders. For example, we could have one binder that has a cohesion of 2 joules per square centimeter at 25 degrees, and another one that has a cohesion of 3 joules per centimeter squared at 15. And the question is, which is better? We can't really answer that because they're done at 2 different temperatures. So there's work to be done specification wise. Sorry, I'm still struggling. When we add polymers to bitumen, it's important that we know when they're mixed together that they're going to stay as a good homogeneous mix, because if the polymer separates from the bitumen on storage, then we get an inhomogeneous system, and the polymers tend to float to the surface of bitumen. If they have the opportunity to separate, they float to the surface, generally speaking. And that leads to an inhomogeneous mix. If you think of a storage tank, if you buy a PMB, you expect polymer to be evenly distributed. If it floats up to the surface, as you start to draw from the bottom of that tank, then you'll be drawing either very lightly modified binder or completely unmodified binder, and it's not going to give you the mix performance that you want. And then as the level comes down, if the polymer is separated to the surface, you will eventually hit a very polymer rich domain, which will either be very difficult to mix or won't pump. So it's important that we have a method of assessing the stability of polymers within bitumen to simulate what happens in storage. And the way we do this is the storage stability test. A peculiar test I would say, because it uses an aluminium toothpaste tube. We place a sample of bitumen into the tube. We try and expel as much of the air as possible so that we don't get any oxidation in the sample. We seal the end of the tube, and then we incubate it. We place it into an oven at 180 degrees for 3 days. Those are generally the most common conditions. You can use others if needs be, but the sort of reference conditions are 3 days at 180 degrees. We then take it out, and as you can see in the bottom picture, we allow it to cool, and then we section it, and we cut it into 3 sections: the top, the middle, and the bottom. We discard the central section. That's not important. And then we test the properties of the top and bottom sections. And we can test the properties of those sections in any number of ways. We can test for softening point and see if there's a difference in softening point. We can test penetration. We can test viscosity. We can use sophisticated techniques. And specifications tend to draw a limit on the difference between softening point top and bottom and needle penetration top and bottom. And a stable binder needs to have less than, let's say, 5 degrees difference between top and bottom. This brings us to another calculation based on 2 slightly different properties, and this is only really applicable for polymer modified binders, but we can measure the difference between ring and ball softening point and frass breaking point, and that gives us a property known as plasticity range, and it effectively gives us the maximum effective temperature range where the binder is going to behave either not in a too glassy or brittle state, or not in a too viscous state where it becomes runny at upper surface temperatures. It's a calculation that's not used a great deal, but it does serve to indicate an effective service temperature range. In the summary, I said we were going to look at conditioning, and we will look at 3 conditioning tests now, to all of which simulate slightly different things. The first 2 that we're going to look at refer to short-term aging, and we use the rolling thin film oven test for this, and it measures the effect of heat and air on the bitumen. In the image that you can see there, you see at the back what's known as a carousel. This holds glass jars of bitumen, and it rolls them around in that carousel, and it makes sure that there's a thin film of bitumen that's in constant motion throughout the test. At the top is a thing called a squirrel cage, and that's there to make sure that temperature distribution within the rolling thin film oven test is very, very good. And at the bottom, you can see a thing that looks pretty much like a snake. It's a coil of pipe, and that allows air coming from either a gas bottle or a compressor to reach the same temperature as the chamber, which is typically 163 degrees, and it directs a jet of air into those samples, those glass jars, as they roll around in the carousel. Now, we measure the effect that this has on the bitumen typically in 2 ways. The first is to measure a change in mass, and that can go up or down depending on the binder. Most commonly, the mass will go down, as during the test we lose some volatile material from the bitumen, but it can, in some circumstances, go up. Or we measure change in physical properties, and that we can do that by, again, by penetration, ring and ball softening point, viscosity. Any of those tests are applicable. The standard conditions for the test are to get the oven and all of the samples together at 163 degrees and carry out the test with air flowing and the carousel rotating for 75 minutes. But you can use other test conditions if you so wish. There's a reasonable school of thought that says for polymer modified binders, 163 degrees is not sufficiently high because polymer modified binders tend to be handled at higher temperatures. There's equally a school of thought that says that for warm mix binders, the temperature should be lower. But the standard conditions that are called up in specifications refer to 163 degrees for 75 minutes. And the rolling thin film oven test is there to really simulate the experience, the aging experienced by a binder during hot mix asphalt production. So we will have work to do when it comes to assessing the aging that occurs during warm mix binder production, and we are working on that. There is another short-term aging method in reasonably common use, which is 12607 Part 2, and this is the thin film oven test. It differs from the rolling thin film oven test by virtue of the fact that there is no real motion. The binder is static, and this particular test is designed to address volatiles lost on storage. So we place our samples of binder into those containers. We heat it up to 120 degrees for 5 hours, or 163 for industrial binders. And again, we then measure the change in properties over that time. It's starting to fall out of favor, is the thin film oven test, as it's being more replaced by the rolling thin film oven test, the RTFOT. Both of those test methods were short-term aging methods designed to simulate either what happens when a bitumen goes through an asphalt mixing plant or when it's stored. And to simulate what happens to a bitumen when it's in service, when it's actually on the road, for example, we need to be more aggressive, and we need to carry out tests typically at under pressure. So we do this using a pressure aging vessel. We place a sample of bitumen, usually that has already been through the rolling thin film oven test, so it's already had short-term aging carried out on it. We place it into the sample pan that you can see in the picture. We put it into a pressure vessel, and we apply really quite high pressure, 21 times standard atmospheric pressure, and we apply heat between 85 and 110 degrees for a period of time between 20 and 65 hours. And then we assess the properties of the binder after long-term aging. And again, we can do that any number of ways. And the pressure aging vessel is there to simulate what happens as bitumen in an asphalt mix ages. People frequently ask, what does it simulate? What does the pressure aging, what time does the pressure aging vessel simulate? And there is no real answer to that because of the variable conditions, different between 85 and 110 and 20 to 65 hours. It's probably safe to say that it gives an indication of the properties of the binder after somewhere between 10 and 15 years, possibly 20 years. That's the sort of range that we're looking at. But we can't give an absolute figure to that because of the variability. We're now going to look at rheological testing. This is the state of the art for bitumen testing as we stand today. Now, I don't want anyone to be scared by rheology, because what it is it allows us to understand fundamentally what happens to the bitumen under the action of different stresses and different temperatures. And rheology tells us why glass shatters, why a rubber ball bounces, why water flows. That's what rheology testing is all about. It's about the study of the deformation and flow of matter. Behind it, there's some really complicated mathematics, but I'm not going to go into that. I'm just going to give you a flavour of what we do. So, the first test that we have at our disposal is the dynamic shear rheometer, EN 14770. You can see a sample being loaded onto the rheometer there. Most rheometers act in exactly the same way. We have a fixed bottom plate and an oscillatory top plate, and we apply oscillating stresses to the top of the sample, and we measure its resistance. We have a black box computer by the side of it that does all the mathematical calculations for us, and in essence, what we can measure from a rheometer is stiffness, or to give its proper terminology, complex shear modulus, G star. We can also measure elasticity using the phase angle, or delta as it's known. And we can also use it to measure things like equistiffness temperature, the temperature at which different binders have the same level of stiffness. Within the rheometer, we measure the behavior of bitumen as a function of temperature, frequency, or of load. Now, it's much more common to focus on the first two and measure the behavior of bitumen as a function of temperature or as a function of frequency. Less common is to measure as a frequency as a function of load. Two most common ways of reporting the data are as a temperature sweep. So here we keep the frequency constant, and for the US that's most commonly 1.69 hertz there, and we vary the temperature, keep the frequency constant, and we vary the temperature, and we measure either the change in stiffness or the change in phase angle across temperatures, and those are called isochrones. Second most common test is what we call a frequency sweep. So here we keep the temperature constant and we vary the frequency, and these are known as isotherms. And what we tend to do is we'll run a series of frequency sweeps and then link all that data together so we can get a full temperature, viscosity, frequency profile across a range of different conditions. You can measure rheology either in oscillation or rotation, and rheological tests tend to relate very well to some conventional properties, and they also give us a good indication of end performance. We could do another test in the DSR, which is called multiple stress and creep recovery test. One of the things that we try to assess, or try to predict, if you like, is what contribution a bituminous binder can play to the resistance to permanent deformation of an asphalt mix. And the state of the art, as we are, is to run this thing called a multiple stress creep recovery test. So we apply a stress to the binder. Yeah, we apply a stress to the binder, release that stress, and see how the binder behaves. And what we find is there's an element of recovered strain and an element of non-recovered strain. Now, that, if we do this over and over again, if we do 10 cycles, we start to build up a full picture of the way that the bitumen is going to behave. We can do it at different temperatures, between 50 to 80 degrees is most common. And we measure two parameters, a thing called the non-recoverable compliance and the percentage recovery. And that gives us, those two parameters give us a good correlation with asphalt performance. It started to be used in specifications in the US as their strategic highways research program has evolved, and it has been proposed for future specifications within Europe as well. We can be more sophisticated in our assessment of low temperature performance by assessing the behavior of a binder or a bitumen in the bending beam rheometer. If you remember, I said that the frost breaking point was a bit limited when it came to polymer modified binders, and that it tended to underestimate their performance. Well, the bending beam rheometer is much more sophisticated, much more accurate than our frost breaking point. Here we take a beam of bitumen and we balance it onto two supports, and we apply a load to it, and we measure the deflection of that beam, going from the image that you see at the top to the one we see at the bottom. You can see the beam has started to deform, and we measure the deformation of that beam. From that, we calculate critical stiffness. Typically, we report when the binder achieves a stiffness of 300 megapascals. All of this tends to be at significantly below temperatures significantly below zero. And we also measure the rate of change of that stiffness with temperature, which is known as the M value. And we can do another calculation there. We can measure a thing called delta TC, the change in critical temperature, and that's the difference in the temperature between achieving a stiffness of 300 megapascals and the temperature at which the M value equals 0.3. So I think that's about an hour's worth of looking at bitumen test methods. What I've tried to do is to give you a bit of history, where we've come from with our bitumen test methods, some practical considerations, particularly in things like penetration, softening point, control of temperature, with the frost breaking point, control of the environment, ensuring that no dust is around and no grease is around, and how those test methods play a role within our bitumen specifications. Next up, we looked at the conditioning methods, because it's important to have a feel for how bitumen ages over a period of time, and we looked at short and long-term aging methods. And then finally, we had a look at rheological testing, which is really going to be the future of bitumen specifications, because it gives an indication of performance, and it gives us much more information about the performance of the binders under different conditions of load, of frequency, of temperature, etc., etc. And within Eurobitumen, we have published a whole range of technical information sheets related to bitumen testing. They cover all of the major test methods that are found in specifications, both conventional and rheological testing. They're available in multiple languages, and they're available for download from the Eurobitumen website. So do go and have a look at those. In addition, we have a YouTube channel which we're looking to populate more and more with information on test methods, specifications, safety, etc. And we also have our data collection exercise, which has fed into a lot of the reviews of test methods carried out within Europe. And so if you need any more information, please feel free to reach out to me or any of my colleagues within Eurobitumen. We'd be more than happy to answer any of those questions. Those are the contact details. That's been a whistle-stop tour through the world of bitumen testing, and I'd like to thank you for your attention.